Today I'm going to be recording the chapter 9 explanation for the notes. And chapter 9 is our last chapter in our chemistry book. So it starts off explaining what are types of bonds. So we can have the ones that occur between molecules and the ones that occur within the molecule. So between and within, those are your keywords. Intermolecular, which means it's between the molecules, like between one CO2 and another CO2. Intramolecular means what's happening between the C and the O in CO2. That's what intra is. Whenever you're talking about intermolecular forces, you represent it with a dotted line, and if it's between molecules, it's VDW or van der Waals forces. And if it's within the molecules, we already know this, like covalent bonds and whatever, it's represented by a full bold line. And now, if it's in a crystal, you have metals, between them you have a metallic bond. And if it's an ionic compound, you have an ionic bond between them. And if it's non-metal elements, like elements and polyatomic elements, like the elements that are made of more than one atom of each element, VDW. If it's a molecular compound, also VDW. If it's a network solid, which are only two examples, are carbon and Si, Si specifically in SiO2, sand or silicon dioxide or quartz, whatever they want to call it, it's a covalent bond. So, and now we have types of crystalline solids, ionic solids, and at their lattice points you find ions. Molecular solids, which you find molecules at their lattice points, which are discrete covalent molecules, that's what you call them. And now you have atomic solids, which are just elements, like pure elements. Metallic solids, which are the ones that form giant structures which are made out of metals. Network solids form giant structures, they're made out of non-metals, but for us we need to know these two examples only. Group 8 solids, they are an atomic bond because they're gases and they're not, like, they don't connect with each other, they're sufficient, they don't need to make bonds. And yeah, so now we have the definition of an ionic bond. It's a strong electrostatic force of attraction between positively charged ions and negatively charged ions. You can read this, I'm not really gonna sit and explain that in that much detail. And okay, so for CQD1, it's asking us describe the structure of NaBr. It's a crystal lattice of Na plus and Br minus, each ion surrounded by oppositely charged ions when they form ionic bonds. Now, their properties are they're hard crystalline solids because they're regularly arranged with opposite charges on top of each other, and they have a high melting and boiling point because it's a strong electrostatic force of attraction between the oppositely charged ions. And they're soluble in water because water molecules, they bind to ions usually, and positive and negative ions, and they don't conduct electricity when they're solid because there's no free moving ions, or there's no free electrons, well, ions in this case. And they're only conduct electricity when they're molten or aqueous, because when they're molten or aqueous, their ions are free and they carry electric charge. They're brittle because they're made out of charges. When you move them on top of each other, it will be like if you had plus, minus, plus, minus, plus, minus. If you move it, you're gonna have minus, minus, and then you're gonna have the plus here, the minus here, and another plus here. These two are gonna repel, these two are gonna repel, so they're gonna break apart easily. That's why they're brittle. Now, here we have which of the following correct properties of ionic compounds. They're brittle, they make a lattice structure, they're hard, they have high boiling points, and they form regularly shaped crystals. CQD 18 now. Sorry, so NaCl, why is it not a solid conductor? And why is it a conductor when it's melted? It's the same reason we explained above, because it's the electrostatic forces of attraction, and when you move them, they start repelling each other. That's why, that has nothing to do with it. The electrostatic force of attraction between them, it makes them not a conductor because they're holding all the ions and you have no free ions. But when you melt them, they have free ions. CQD11, it's a regular pattern of negative ions, Mg2 plus and Cl, positive and negative ions, which are Mgc plus and 2O. Yeah. Now you have covalent crystals. These are really easy, just read them. And now you have CQD14, explain why aqueous solution of sugar is non-electrolyte and when NaCl is. Because sugar does not have any ions or electrons whatsoever. NaCl has it. When it deassociates, it makes ions. Sugar has no ions, so it's not an electrolyte because it has nothing to deassociate or to hold or carry electric current. Metallic bonding, just go over to the definition, this definition here, and if you write this, you're gonna get a guaranteed mark for CQD20. For this, read it, it's really important, this table. CQD4, it's telling us that sulfur is not a conductor, while sodium is a conductor. Sulfur is not a conductor because it has no free ions or electrons that can move and carry current, so it's a non-conductor. Whereas NaCl, due to its mobile sea, or like Na, not NaCl, sorry, my bad. Na, due to its mobile sea of delocalized electrons that can move and carry electric current, so making it a conductor. Silver is shiny because the free electrons, they absorb light and re-emit it. CQD6, explain why sulfur is brittle while copper is ductile and malleable. Sulfur is brittle because it is held by VDW, which are weak attractive forces of attraction, whereas they're really weak. But copper, it's held by metallic bonds, which are non-directional bonds that form without shattering the structure when you move it. That's why it's malleable. Now, these are the 4 properties: shiny, good conductors, high melting and boiling point, and malleable. And this is an example, not really important. Examples, not really that important again. And they're just here telling you an allotropy, when 2 or more form of an elements exist in the same physical state. So when they're made out of the same elements, yet they have a different structure. That's what you call them. Now for carbon, it's diamond, graphite, and Buckminster-Fullerene. Yeah, however the hell you pronounce it. So diamond, it's held by 4 other bonds. It makes 4 bonds with each other tetrahedrally. You need to memorize how their structures are. So it has very high melting point, very hard, not electric conductor or thermal conductor. Graphite, it's held with 3 in a triangular shape. It's soft, slippery, good conductor of electricity, and high melting point. Why is it a good conductor? Since it's held with only 3, there's 1 left that's delocalized and it is just moving freely. And these are tables, you really need to read them. They're very important, these tables. Yeah. So now we have CQD19. It says to describe the structure of a network solid and give 2 examples. Now, as you can see here, network solid is a giant 3D structure made of millions of atoms held by strong covalent bonds where the shared electrons are localized between the atoms, which means that the shared electron, the electron that's in the middle, it is between the 2 elements holding it together. So their structures are very rigid. For these examples, I can't really help you with them. They're just purely reading the notes and you'd know them. And just continue reading the rest of the answer. Now, which of the following is a not common property for diamond and silica? Each of their atoms are surrounded by 4 covalent bonds. No, actually, because silica is surrounded by 2 double bonds. That's why. And as you can see here, it's explained. D, because every O atom is bonded to 2 Si atoms, not 4. So yeah, sorry. And now CQD2, it's asking us why the sulfur melt at a lower temperature than graphite, because it is held by VDW, which is easy to break, making it have a low and melting and boiling point, whereas diamond has strong covalent bonds. The covalent bonds are the strongest. Since they're strong covalent bonds, they have a high melting point. And the same thing because they're held by VDW, which is easy to break, whereas covalent bonds aren't so easy to break for CQD3. Now CQD9, this is genuinely a really long question. Let me pull it from the answer sheet. I'm sorry, I was explaining and I didn't realize it wasn't recording. Anyways, so for CQD9, it's asking us about germanium, which has a similar structure to diamond. So what they're telling us in this question is just describe the structure of diamond because it's the same as the thing they gave us. So it exists as a giant structure where each atom is connected to 4 other atoms in a tetrahedral arrangement, and it's a really strong arrangement. It's really strong covalent bonds. And silicon dioxide, it's also similar to that of diamond, but it's not that similar because it's made out of 2 more elements. So it's made out of, silicon dioxide is SiO2. So it's a giant covalent molecule where every silicon atom is covalently bonded to 4 oxygen atoms in a tetrahedral structure also, and every oxygen is strongly bonded to 2 silicon atoms. It's the ratio from 2 silicon atoms to 4 oxygen atoms makes it 1 silicon. For every 1 silicon you have 2 oxygen atoms. In CQD1 they're asking you the intermolecular forces between each in the crystal. Anytime it's a gas or any diatomic gas like H2 or He or O2 or not, C is different because it is a network solid, so it's a covalent bond. Na is a metal, so it forms metallic bonds, but anything other than that, it's always gonna be VDW. Always. Just don't think about it. So it's like usually always VDW unless it's in the specific cases where it's a metal or a network solid or ionic. Now, CQD10, it's actually not with us, it's not required, nor is example 8. Now for CQD12, it's the same question we had before, but now we want the type of solid and the particles making it up, not the bonds. So for CO2, it's a molecular solid because it's a molecule, and the particles making up the solid, if it's molecular, is molecules. I2 is also a molecular solid because it's made out of molecules, and also particles making up the solid are molecular. KCl is ionic, and since it's ionic, the particles that make up an ionic compound are ions. Diamond, we know it's a network solid made out of atoms of carbon bonded together by covalent bonds, so making it a network solid that is bonded by atoms. And H2O is a molecular solid made out of molecules, of course. Li, metal, it's in group 1. It's a metallic solid, so it's made out of cations surrounded by a sea of delocalized electrons that can move, of course. Xenon is xenon, it's a special case. It's because it's a noble gas, and noble gases, they don't bond with anything other than themselves. They don't bond with anything because they have a full shell of electrons. So for xenon, since it's a group 8 element, it's made out of it's an atomic solid because they don't bond with anything. It can't make molecules, and since it's atomic, it's gonna be made out of atoms, of course. SiO2 is another type of network solid, and it is made out of atoms. So atomic solids and network solids are made out of atoms. Metallic solids are made out of cations in sea of electrons. Ionic are made out of ions, and every molecular is made out of molecules, of course. Now for CQD13, they gave us a list of electron distributions, and we need to tell them which is which. So for this question, your key thing is looking at the valence electrons to know in which group it is. Now, they're asking you which of the following is a noble gas. We know noble gases always end with valence electrons 8. So D is the only correct answer. Now, is a soft metal with low density. We know metals are groups 1, 2, and 3. And transition metals, of course, but mostly 1, 2, and 3. So how do we know if it is in 1 and 2? Because these are the only 2 metals we have. But if it's with low density, then you're gonna choose definitely the one with the lower group, because as you go up in groups, they get increase in density. Now, which of the following can form a covalent compound with element A? So element A is in group 5. If you want to form a covalent with it, you need to choose another non-metal. And the following non-metals that you have, we could make it with, since it's in 5, we could also make it with 7, because 7 is not a noble gas and it bonds with other elements, and it's also a non-metal. Now, so that's in F. Now, for which of the following has a giant molecular structure similar to diamond? So basically they're asking you which of the following is in group 4, because we know network solids only form from group 4 elements, which the only one that ends with 4, which means it's in group 4, is B. Now, which of the following form negative ions, which means which of the following is a metal, but they want 3-. So if it's in 3-, it means it has to be in group 5, of course, to form 3-. So that's A. Now, moving on to the next CQD, CQD 23. So CQD 23, they're asking us, they gave us macromolecules, they gave us their melting points, boiling points, electric conductivity in solids, liquids, and solubility in water. And we need to know now which is which. Now, which substance is a metal? Now, we know metals are good conductors in solids as their solid state and their liquid state. The only one that's a good conductor as its solid state here is E. So that's your metal, of course. Now, which substances are ionic? Why did you choose these substances? Now, how do you know ionic compounds? If they are not a good conductors in solids, yet they're good conductors in liquids, then they're ionic. So our only two examples are A and B. Because they're not good conductors in solids, but they're good conductors in liquids. So A and B are your answers. Why? Because they don't conduct electricity as solid, yet as liquid they do. That's the answer that I wrote. Now, which of the substances conducts electricity in aqueous solution? How did you know this? You're gonna say, oh, A and B again. No, it's not. Because why? In an aqueous solution means dissolved in water. And when you see dissolved in water, you can't have something insoluble dissolved in water. So the only one that's a good conductor in liquid and is soluble in water is A. So A is the one that can conduct an electricity in aqueous solution. Which of the following is a gas at room temperature? You're gonna look for the one with the low melting and boiling points, which is D, because D, by the time it reaches room temperatures, which is 25 degrees, it would have boiled, because 25 is definitely less than negative 56.6. Or sorry, 25 is definitely more than it. So by the time it's 25, it would have boiled to become a gas. Now liquid, it's the same thing. It has to have a very low melting point that's below 25, but a very low melting point, but a boiling point over 25. So it is a solid. This one is like in the middle. Now, which of the following is a network solid? Network solids, we know they have very high melting and boiling points, and they are not good conductors when solid, nor when liquid, and they're insoluble. The only example we have here is this: not good conductor, and insoluble. Now, a student thinks that it is graphite. Do we agree with him? Definitely not, because graphite, we know it is a good electric conductor when solid. Since this one is not, it is not graphite, definitely. Now for our last CQD, which is top question 24, it's telling us potassium nitride melts at 800 degrees Celsius, nitrogen trifluoride melts at negative 200 degrees Celsius. Why, in terms of attractive forces, did potassium nitrate have a higher melting point than nitrogen trifluoride? And you have to refer to the type of attractive forces between them. So potassium nitride is ionic. We can tell this because one of them is a metal, the other is not. And when it's an ionic bond, it's between negative and positive particles. And we know ionic bonds are very strong, stronger than VDW, yet weaker than covalents. Now, nitrogen trifluoride is a molecular compound because it's made of two nonmetals. So they have weak intermolecular forces called VDW, of course. Ionic bonds are much stronger and they require more energy to break them up, so it will melt at a higher boiling or melting point. Now for this is a table my teacher drew in class when she was explaining this. It can help us like a lot when memorizing. So we know ionic bonds, let me change the color to red. So ionic crystals, they're made of ions and they're held by ionic bonds, and at your lattice point you're gonna find ions. This isn't anything new for now. Oh my gosh, I need to redraw it. So ionic, ions, ionic bonds, their lattice points you find ions, and these are examples. Covalent, they're molecular elements, so discrete molecules, you can call them both. They're held by VDW forces, and at your lattice point you find molecules. So their basic unit is molecules, practically, and these are a lot of examples. Now atomic solids, you have three types. You have metallic, you have network, and you have group 8. Metallic are metals. they're held by metallic bonds, and they're in cations in a sea of delocalized electrons. And of course, you know your examples. Network solids, we know our only 2 examples are diamond, graphite, and SiO2. Diamond and graphite are both made out of carbon, and yeah. And network solids are made of atoms. They're held by covalent bonds. At your lattice point, you find atoms, and yeah. Now, group 8 are atomic solids. They're held by VDW. They find atoms at their lattice points, and you find them in group 8, of course. And that's it for chapter 9. The periodic tomorrow should be easy. Remember, of course, CQD10 isn't with us. And there's a point about polar and non-polar bonds. Now, we don't have any examples with us other than CO2. All you need to know, it's a non-polar bond. And that's it. Hope you understood everything. Have a good day. Bye.